Hello everyone, welcome back to the series of tutorials on geostatistics. Today we will learn the important concept of two-point statistics. More specifically, we will learn about variograms and how they can be used in a particular way to estimate probabilities as a function of distance to some reference object. Here's the problem that we'll be addressing today. Suppose that we have a microcity image of a rock sample, such as the Caton image kindly provided by the Perm Research Group at Imperial College London, and that we wish to estimate the average grain size within the sample. So if you look at this Caton image, the grains are colored in this yellowish color, and the empty space between these grains is colored in this bluish transparent color. The average grain size can be an important parameter for subsurface characterization, yet assigning a single value for the sample objectively is not always trivial. These grain sizes can vary considerably, and it's not easy to assign a single value by just visually selecting a subset of these grains. Our goal is then to estimate the average grain size or average grain radius in this rock sample. Can we do any better than visual estimation? As usual, we load the GeoStats package for the calculations and the GeoStats images package to load the Caton image into this variable here, k. This image has this number of voxels, and it has a single spatial variable in it, the grain, which is 1 whenever you are inside of a grain and 0 otherwise. In order to address this problem, we need some theoretical background. We will solve this problem by estimating the probability of observing grain at two locations, U and V, in that rock sample, and by understanding how this probability changes with the distance h between these locations. Consider two binary or Bernoulli random variables, ZU and ZV, that indicate grain with some probability P and non-grain or empty space with probability 1 minus p at these two locations, U and V respectively. The variogram between these locations is defined as this quantity here, is half of the expected value of the square difference between these two variables, ZU and ZV. We can use the linearity of this expected value operator and open this expression as the expected value of ZU squared, ZV squared, and this cross term ZU times ZV. Because these variables are binary or Bernoulli, we can further derive expressions for these expected values in terms of probabilities. For example, the expected value of ZU squared is the expected value of ZU times ZU. And if you open the expected value as the sum of all possible combinations of ZU, which in this case is zeros or ones, the only term that's not 0 is when both ZU and ZU are 1. Or equivalently, it's the probability that ZU equals 1. Or in words, it's the probability of observing a grain at location U. The expected value of ZU times ZV can also be derived by observing that the only term of the expected value summation that's not 0 is when both ZU is equal to 1 and ZV is equal to 1. ZU and ZV are not independent, they are spatially correlated. So in order to derive this as the product of two probabilities, we need to use the conditional rule. So we say that the probability of observing grain at U and observing grain at V is equal to the probability of observing grain at U times the probability of observing grain at V, given that I already know that I have a grain at location U. Similarly, we can derive the expected value of ZV squared to be the probability that we have a grain at location V. Now, we know that the probability of observing a grain at location U and V are equal to P, the parameter of the Bernoulli we have chosen above. So we can rewrite our variogram for this distance h as this expression here, when we substitute all this expected value by the corresponding probabilities here. We further rewrite 1 minus the probability of having grain at V to be the probability of having empty space at V here, given that location U is known to have a grain. So we can rearrange this term and express this 2-point probability here, which is the probability of observing an empty space at location V, given that I have a grain at location U, as the ratio between this variogram quantity that we didn't explain in detail and this marginal probability of grain. We don't need to understand the details of this variogram in this tutorial. Upcoming tutorials will cover variograms in more detail. But the message here is that this equation is telling us that we can efficiently estimate this 2-point probability if we have efficient methods and algorithms to estimate the variogram and the probability, P. The good news is that efficient algorithms, parallel algorithms for variogram estimation do exist. Here we will be using the algorithm we proposed in 2019 for partition variograms. We will consider here 1 million samples from this Canton rock for demonstration purposes of the computational performance of GeoStats. So here is what I will do. I will create a spatial sample from my Canton rock, and I'll take 1 million samples from this rock without replacement. So this is a data view with 1 million grain measurements. And we know that due to compaction and other physical processes, these grains, they're not actually perfect spheres. They're ellipsoids or spheroids with major and minor axes. So knowing this, we would like to characterize the axis of these grains on different sections of the rock, vertical sections, horizontal sections, and so on. So we can, for example, consider planes or sections that are normal to some vertical direction. So here what I'll do is I'll create a spatial partition of my samples, and I'll partition them with a plane partitioner, where I specify the normal direction to the planes. In this case, I can say the vertical direction here, 0, 0, 1. So this partition has 256 planes, and that's what we have seen here. The model has 256 by 256 by 256 voxels. So in the vertical directions, we have 256 planes. And each of these planes has a number of points from our spatial sample. We can, for example, plot some of these planes to observe them here in a plot. So plot the first plane, the second, and the third, which do not necessarily are in order of depth, because this partition algorithm is efficient and doesn't necessarily preserve the order of these planes. It takes some time to plot because that's the first time you're plotting. But here you can see, for example, 3 planes taken from the Canton rock, from the samples, from the 1 million samples of the Canton rock. The yellow color is the grain, and this blue color is the empty space between the grains in these 3 planes that I have plotted here. Now we can efficiently estimate this variogram quantity on these planes with this partition variogram algorithm. Because there are many options to this algorithm, we can always access the documentation by pressing Shift Tab Tab and then opening this documentation here, for example, to guide us on the selection of the arguments. So as you can see in the documentation, this is the empirical variogram of a spatial data set for some variables, var1 and var2, or alternatively of a partition here, which is according to our paper published in 2019. So we can, for example, take our planes and calculate the empirical variogram of the grain variable. I will time here so that you see that this algorithm is quite efficient. We have 1 million points in this data set, which are arbitrarily located in space. There is no regularity or any grid assumption. And still, we can perform this calculation in 14 seconds which is a parallel implementation with multiple threads. I have 8 threads running in this machine. The number of evaluations of this variogram is this number here, which is 107 million evaluations, and that took 14 seconds to calculate. We can perform both these steps, let me close this documentation, in one single shot with this planar variogram type. So I can say the planar variogram of a normal direction, so I'll say again the vertical direction. Now instead of passing the partition, I can pass my original samples, and I can specify again that I want the variogram of the grain variable. I'll save this into a variable here, the empirical variogram, and I can plot this variable so that we observe this variogram quantity as a function of the distance. So this will create the partition P that we did above, and then we run the parallel partition variogram algorithm on that partition. It will take around 14 seconds again. And so this is the empirical variogram as a function of this distance or lag age. This procedure estimates this variogram for a fixed set of bins here that you're seeing. So we only have the value of this variogram estimated at these dots. In order to be able to evaluate this variogram at any distance h, we can fit a variogram model, a theoretical model. If you are familiar with variograms, and we can cover this in future tutorials, you will know that this variogram has a very exponential shape. So I'll create my theoretical variogram, which is fit of an exponential variogram to my empirical variogram. And this procedure will run a weighted least squares method to estimate this exponential variogram. So we can plot our original empirical variogram as above, and I'll give it a label empirical. And I can also, on top of this, plot my theoretical variogram, for which I'll give the label theoretical. This theoretical variogram is plotted by default until like 3 times the value of a quantity that's known as the range. So I'll just say plot it only until 30, for example, lag distance. I'll also give it a color that's green here, so that's easier to visualize. So as you can see, our empirical variogram is shown here, and our fitted exponential model is shown in green. The second step in order to estimate those 2-point probabilities is to estimate the probability P from the data. So we can estimate this probability P by simply taking the proportion of grain in that rock sample, which is the mean on our spatial samples of the grain variable. So we have 87% of the rock as grain. Finally, we'll create our scaled variogram that I will call here gamma P, which is our theoretical variogram scaled by this marginal probability P. So we can now plot our probabilities that we are seeking in the beginning of this tutorial, because this scaled variogram is exactly and theoretically equal to this probability of having empty space at location V, given that location U is a grain. So I can plot my scaled variogram. And as you can see, this is showing that the probability that 2 locations U and V have a different value, for example, the probability that location U is a grain, when location V is empty space, is 0 when U coincides with V. And as we make V go further and further away from location U, the probability of hitting an empty space increases. However, this probability doesn't increase indefinitely. It reaches this plateau here. This plateau is known as the seal of the variogram. So I can plot, for example, a horizontal line at the seal of my scaled variogram. And I'll give this a dashed line style so that it's easy to see. The distance at which we start to reach this plateau is known as the range of the variogram. So I can plot a vertical line on the range of my scaled variogram, and I'll also give it a dash line style. So let me give a label here to the seal of the variogram. So if you stop to think carefully, what is this value of probability that we reach after certain distance? If you think of two locations, U and V, and you make location U a grain, which is your reference location here, and you start moving V away from U, it gets to a point where the chance of hitting an empty space is just the chance of finding an empty space in your entire rock sample. It doesn't matter anymore that U is a grain. It's too far from U, the location V. So actually, this value here that the variogram is converging to, is the marginal probability of empty space. So I can say here that this is the value 1 minus P, which is the proportion of non-grain in the image. I'll also give this a label, which is the probability of ZV equals 0, given that ZU equals 1. And finally, we need a label for this vertical line here. So this vertical line here, think about it carefully. So we start increasing the distance between locations U and V, and at some point this probability is just the marginal chance of hitting an empty space. So this boundary distance, where it doesn't matter anymore how close you are to the location U, can actually be interpreted as some average grain radius. So I can say that this is actually the average grain radius that we are after, which in this case is about 20 voxels of distance. And that's what I'm saying here in this text. The probability levels out at some positive distance, which is known as the variogram range, after which the chance of encountering a non-grain at location V, given that location U is a grain, is simply the marginal probability of non-grain. And you can actually check that this is the case, because if you look at the seal here, the value is 0.12 something, and the marginal probability is also 0.12 or something. I can also calculate the seal here so that we see this, which is very close. So we define our average grain radius on these horizontal planes or horizontal sections of the scatum rock. We can create a function that summarizes all that we have done for this horizontal direction, and now generalize this to any section, horizontal, vertical, or even diagonal planes of the scatum rock. So let's create a function to compute this radius. So I'll call this the radius as a function of the normal direction. The first thing we will do is to compute the planar variogram of my spatial sample, right? And the first argument of this planar variogram is the normal, and the variable that I'm interested in is the grain. I'll save this in our empirical variogram. The second step is to fit a model. We know that the exponential model in this case seems to be a good model. So I'll fit it to our just estimated empirical variogram. And then we need an estimate of the marginal probability of grain, which we got from the mean of the grain, the proportion of grain in this rock. And finally, we have our scaled variogram, which is 1 over p times our theoretical variogram. This is our scaled variogram, and we define the radius as the range of this variogram. So this creates a function that we can call for different normal directions, so that we can estimate the average grain radius on planes that are horizontal and planes that are vertical, for example. So I can say for the normal direction in 1, 0, 0, so planes that are perpendicular to the x-axis, 0, 1, 0, and 0, 0, 1. Let's compute the radius for this normal, and now print, for example, the normal direction, and then the radius that I obtained for this normal direction. So when I execute the cell, we'll be computing this average radius for planes perpendicular to x, planes perpendicular to y, and planes perpendicular to z. Oh, I have a typo here. Let me fix that. And so this will take approximately 14 seconds for each of the directions. And it may take a different time in your machine, depending on the hardware you have at your disposal. So we see that for the planes perpendicular to the x direction, the average grain radius is 18. And for planes that are perpendicular to y, we have also 18. And as before, for planes that are perpendicular to the vertical direction, we have 20 average grain size. So this difference between horizontal and vertical radius is due to physical processes, compaction, and so on. And we can visualize this anisotropy if we choose a set of vertical planes and estimate the variogram for all directions on this plane. So what I will do here is use another object called an empirical varioplane. I can also recur to the documentation again. So this empirical varioplane will take the vertical direction that we want. For example, the normal direction that we would like to investigate would be the x direction to produce vertical planes. So let me set this already. So the normal will be 0, 0, 0, actually 1 here, the x direction. And then I can compute the empirical varioplane of my spatial sample for the variable grain. I can also specify the max lag to be 30 of maximum lag, and that will create our empirical varioplane object. So this will take some time, because what this procedure is doing is splitting your spatial samples in vertical planes that are normal to this direction, then going for each of these planes and splitting these planes into various directions, various angles, and computing the variogram for all of these angles for each of these planes. This is a very computationally intensive process that's only possible because of this algorithm that we have developed for partition variograms. So while this is running, we can actually plot our empirical variplane and plot it using a model that we know to be an exponential variogram. It should take around 1 minute or so to finish this calculation. So as you can see here, this empirical variogram was calculated for various angles on those vertical planes. So for angle 0, we have this amount of calculations, and we have all angles until angle 180, because we have a symmetric calculation. So for angles above 180, we can just mirror the values we learned from 0 to 180. So let me plot this here at the bottom so that we have an idea of what's happening. So this is the empirical varioplane plot, where each of these angles here is an angle that was taken into this vertical plane. So you're looking here at some vertical plane, and here you're looking at some horizontal direction on this plane, for which we have estimated this average grain radius to be the 20 we've seen before. As we move the angle and go to this 9-degree angle, we're looking now at a vertical direction, and we've seen that the average grain radius in the vertical direction is a bit smaller, around 18. So that gives this ellipsoid shape or average grain shape for the grain. We have a few remarks to finish this tutorial. We've learned that variograms can be useful to efficiently estimate these 2-point probabilities. We've shown that the variogram range represents the average grain radius of these grains in the rock. Here there's this hidden assumption that these geobodies or shapes are ellipsoids. This interpretation and calculation do not work when you have geobodies that are channelized or curvilinear. GeoStats provides these variogram estimators that are very efficient and run in parallel and can handle more than 1 million points arbitrarily distributed in space. For more details, please check our paper called Efficient Variography with Partition Variograms. Hope you enjoy it, and see you in the next tutorial.